So with problems where we're trying to optimize a value, we did this one yesterday. What we're trying to do in this problem here was optimize the cost. So when we say optimize, that's a fancy way of saying we're either trying to maximize something or minimize something. All right, when we're dealing with something like cost, obviously we would want to minimize our cost for something. If we're talking about something like profit, we would want to maximize something like that. All right, so these optimization problems are looking for minimum values or maximum values of some function. The trick is you're going to have to figure out a lot of times what that function is going to be based on a situation that's given to you. So we went through a lot of these steps that I have up here yesterday. So this is just kind of formalizing what we did. This isn't necessarily like exactly what you're going to do for every problem, but it's kind of got the idea of it. We did all of these things with the exception of number one with yesterday's problem. Number one said set up a model. That model was actually set up for us on this problem here. That's this right here. This equation is the model that I'm talking about. So it's basically a function of two variables in this case that gives us a cost. Okay, so when we set up the model, we're going to have some kind of equation, and we're also going to need to know what those variables represent within the problem. So we're going to set up a model, make sure the variables are clearly defined. This kind of goes along with number three also for writing a function for the quantity that we want to optimize, minimize, or maximize. So we want to set up a model. We want to figure out what's the biggest possible value and the smallest possible value for the variables that we're using. And then we want to set up a function. Usually that function is going to be in terms of more than one variable. So if that's the case, we're going to use some relationship that's given to us. In the problem, the relationship that was given to us was the volume of this swimming pool-like tank that we were building. And so using that, we could figure out how x and y are related to each other. And that allowed us to eliminate one of the variables. So we're writing it just in terms of one variable. Then we identify candidates. So we figure out, okay, what are the endpoints? What are the possible critical points on the interval where the derivative of 0 or undefined? And then once we have that, we choose the one that optimizes it. We also want to justify why it's a maximum or a minimum. So yesterday we justified it using the first derivative test. That worked yesterday because we saw that the cost was always decreasing up to 15 feet, and then it was always increasing after 15 feet. So since there was only one sign change, that works. If there's more than one sign change, or maybe not any sign changes at all, then the candidates test would be a better option. Okay, we could have used the candidates test here. The endpoints that we would have identified as candidates, though, would have been 0 and infinity, which wouldn't really have been, they wouldn't have made sense for that problem, because we would have had a tank with 0 depth or 0 width, and neither one of those make much sense. All right, those would give us infinite cost. Either way we did that. The important thing about step number 6 here is we support our answer using calculus. All right, so we're using something like the first derivative test. I didn't put it on here, but you could use the second derivative test if you wanted. But remember, the second derivative test gives what? What kind of extrema? Local. So if we use the second derivative test, you'd have to be very convincing that it's also a global or a global extreme value too. So the candidates test is usually the one that we use for global extrema, but there are some situations like yesterday's problem that the first derivative test works.